Yeah. Mr. G Math coming at you live, 7202, less than 32. Woo. I feel like this is like Star Trek, like I'm like doing like a log. Log number, June 29th at 9:15 in the morning. And we're learning about more rules of knowing how to take derivatives. So this is the product and quotient rules. So as you can guess, it's a rule used if you have two things multiplying or two things dividing, correct? So I want you to look at the formula, if you like to think of it as a formula or a pattern of how to do it. So first of all, when do you use this rule? Is when you have two functions what? Multiplying. You with me? All right. So you have f times g. The pattern is actually pretty intuitive in some sense. So here's the pattern. It's the first times the derivative of the second plus the second times the derivative of the first. Let's try it again. So when you multiply, and if you say it out loud and think with me, it is an intuitive formula. Like the quadratic formula is not intuitive, right? You got to sing your song. This is intuitive. It should flow like a river. So, f times g. How do you take the derivative? It's the first, if you guys say it out loud with me, it's on the video. It's the first times the derivative of the plus the second times the derivative of the first. You guys weren't all participating. I can hear it. So, f times g. What's the rule? What's the formula? What's the pattern? You ready? So when you multiply, how do you take the derivative then? So, and you can tell this is going to save us time because otherwise we have to distribute, do all kinds of stuff. Here we get it right away without having to do algebra first. Okay, so again, multiplying. How do you take the derivative? It's the first times the derivative of the plus second the derivative of the first. Now we're participating. Now, quotient rule. So we use the product rule when we're multiplying and the quotient rule when we are dividing. This is also intuitive, but has a little more to it than the product rule. So the quotient rule is when you're dividing. So in this case, it's f divided by g. It's going to be a fraction. And in the numerator, it's the bottom times the derivative of the top, subtract the top times the derivative of the bottom, and then it's the bottom squared. This one is not as, right, not as intuitive, but there is a pattern, right, to it. So again, when you say it out loud, you might actually believe the rule. You got it? So when you're dividing, what's the rule? And the best thing is you have to start here. You must start with the bottom. When you're using the quotient rule, where do you start? Where do you start? Bottom. That's right. And there's, right? Because it's the rule. And this is a good point, Jared. Not like I don't want to show you exactly the proof and everything else. Do you know how many proofs are on the Calculus AP exam? And the answer is none. 0. They don't ask for one proof to know why a rule works or anything like that. If you go to university and a prof hates you, he could go through all kinds of calc proofs, right? But right now, here's a rule and we're going to learn it, okay? So, when do we use this rule? Is when we're dividing, right? What is it? So, f divided by g, right? Top divided by bottom. What's the rule? What do we start with? Bottom times the top, right? The derivative of the top. Subtract. Does that make sense because you're dividing? Then it's the top times the derivative of the bottom all over the bottom squared. Let's try it one more time. The quotient rule is the what? Times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. Let's say for the product rule, you get the order wrong. Instead of going first times the derivative of the second, you want, I forgot, I think it's second time whatever, right? And you get the order wrong, it won't matter. It would be the same answer either way, right? Because when you multiply and add, order doesn't matter. So let's say you take the derivative first times the second, who cares? But for the quotient rule, does it matter when you're subtracting and dividing order? Order matters. So you have to start with what for the quotient rule? The bottom. times the derivative of the top. And you're subtracting, and think of that, right? In terms of dividing and subtracting go together. And then the bottom is squared. All of these rules you remember by practicing, right? Sure?
So it's the bottom times the derivative of the top?
Yes.
How do you do that?
We're going to practice it. You ready? Now, do you see in the box how they used F and S? That's first and second, and they used B and T for bottom and top. Okay? As an informal way, right, to remember the rule. But right now we're going to do it, okay? If we don't practice and put it in context, you're not going to remember a formula. So number one, which rule would I use? Now, if we didn't have a product rule, you would distribute, right? Combine like terms and then do the power rule.
Yeah.
Sometimes that's still okay. There are times that doesn't save you much time.
Wait, so f of g isn't always going to be an actual equation, like their own function? It's just going to be like terms?
Two things multiplied. Mm-hmm.
Right.
And so when you see a product in there, you know you can use the product rule. So what would the derivative of f at x be? So let's start. It's the first, which is 3x squared minus 2, times the derivative of the second. So first and second. What's the derivative of 2x plus 3? 2. Plus, I'll put it underneath here, the second, which is 2x plus 3, times the derivative of the first.
6x.
Let it go. So once it's algebraically equivalent, let it go. There might be questions where there's an advantage to simplifying it, and you have to do more things with it. But if all you're asked to do is take the derivative, then once you hit algebra, you stop. Okay? It's the calculus. So you want me to go through number one again?
Yeah.
So do you recognize the first and the second?
Yeah.
So the rule is first times the derivative of the second. You say yes.
First.
The first is what? 3x squared minus 2. What's the derivative of the second? 2. Can you see I'm multiplying it? So what's the rule again? First times the derivative of the second. And I see I did that, right? Yes? And then plus the second, which is times the derivative of the first. And you're going to get a chance to practice this. Okay? 2. We haven't done the quotient rule yet. Here we go. Y equals. So the derivative, y prime. We're going to draw a beautiful long fraction line. And you are getting over that phobia. And it won't matter here because we're not simplifying it. We're just applying the rule. So the rule starts with what? The bottom or the top? Bottom. Yay. So what's the bottom? And we're going to use parentheses. 2 minus 3x times. What's the derivative of the top? 4x minus 4 minus what? The top.
Times the bottom.
Top. 2x squared minus 4x plus 3 times the derivative of the bottom, which is, and then the bottom squared. Done. You don't want to do algebra there first. Like to simplify that, to try to do derivatives with the power rule. So can I go over it again, number 2? Are you listening? So do you recognize what's on top and what's on the bottom?
Yeah.
The rule is bottom times the derivative of the top. You say yes.
Yes.
Subtract.
C.
The top times the derivative of the bottom all over the bottom squared. That's the rule. You just got to practice. And then the last one, I don't want you to use any rule but this rule. So the only reason we would use a product or quotient rule is because it makes it simpler. Not because we're doing it just because we're doing it. So how would you take the derivative of number 3? You would write it as an exponent and then do the power rule. Why would you use the quotient rule there, right? Negative 2 times negative 9 is positive 18 over 5. X to the negative 3. So for number 3, it's like, don't forget, if you can do the power rule, that's always the quickest, best way of doing a derivative. Why do we have other rules when it's not so simple to write and do the power rule? Now we have other ways to quickly do it. And notice I didn't mess with simplifying, combining like terms, or any of that. You might have to. You might still have to have that skill. But if you don't have to, you don't have to. All right. Calculator differentiation. You know what I learned yesterday about Desmos? It does derivatives really easily. Can I show you?
Yes.
Okay. So it says TI 8384. This is like, that's 100 years ago. So you are going to get an Inspire most awesome calculator soon enough. Last year's calculus used a TI 89, which is what this looks like, which is great. That's what I've been using last few years. So I want you to open up Desmos. What's that? You check it out like a textbook, so you have it all year. At home, everywhere. Just be careful. It's not cheap, so it's, $200 or whatever, right? But a textbook is like that too when you lose it. Did you know that? So, anyways. So can you open up Desmos? I'm going to type in the function given in number 4, as is. F at x equals x cubed plus 3 to the x. Now, this is going to be completely different when you get your graphing calculator, but it's kind of interesting to know that Desmos can do some calculus. So did you type that in? What's the symbol for derivative?
Prime.
Not cool? So if I wanted to look at the graph of the derivative, right, I could take off f at x. What does the graph look like for the derivative? Why is that powerful? Because if f at x described the motion of a particle, right, can you see where it's decreasing and increasing?
Yeah.
Where does it change direction?
Whatever that one is.
Right there, right? And it changed direction from increase and decrease and so on. So Desmos can do that. Now, in the question it says, what's the derivative at 2 using your calculator? Well, guess what I put in for x instead? And what's the answer?
21.
That's it. Write it down. And it's okay to truncate. That means 887, done. That's truncating. It's okay. Okay, can you do number 5? Using Desmos. So in this case, and again, Desmos doesn't care if you use g at x or f at x. So I know, it's the bomb. So g at x is ln, and it likes ln, x squared, subtract 3, correct? What does it ask you to do? Can you find g prime at 2? Is that super simple with Desmos? And the answer is 4. What does that mean? When x equals 4, is the function increasing or decreasing? Oh, 2. It's increasing. Why is it increasing? Because the derivative is positive. That's simple. If the derivative was negative, it is decreasing, right? You have a negative slope. That's simple. How about g prime at, oh, this one should be 4. At 4, what is it? What's the answer?
What's all that stuff in the middle? Oh, and derivative?
Oh, in terms of, yeah, that's calculator talk for the 83, which you don't need to know.
Oh, okay.
So the n derivative, it's teaching, if you had a TI 83 or TI 84, then you could do calculator, whatever, and get the same answer that we're doing at Desmos very intuitively. The calculator you're getting is very intuitive, like that. More intuitive than this. So, I don't think it's touchscreen. What's with touchscreen? It just makes the screen yucky. I don't get it. 0.615. Now, if I asked you about the acceleration of this, do you notice that it's still increasing? But it went from 4 down to 0.615. So the acceleration is actually deaccelerating, right? It's still increasing, but at a slower rate. What do you think the graph looks like?
Like that.
Nope. What does the graph look like? Take off the first one. Just look at the second one. And what does the picture look like for the derivative? What would be a good window? I'm going to go from all the 6's. So,
Infinity.
hmm?
Infinity.
No. So window from -6 to +6, -6 to +6.
Oh, right.
And then what does it look like? So let's put this back on. So can you see what the derivative looks like? Can you take the, well, should I say, is this what am I going to say? Can you take the derivative everywhere?
Can you what?
Is it a continuous function?
No.
So you can't take the derivative where it's not continuous, right? In fact, in this case, from -1 to +1, there's nothing there, right? You can't take the derivative there. So it's just beyond there. All right, what's number 6 there? What's the derivative at 0? And you already know this without a graphing calculator. Does anyone remember from yesterday? What does this graph look like? Correct? Where's this vertex when x equals what?
0.
So, what's the derivative at 0? Why doesn't it exist? Let's do
It's
the...
the chunk or the chip, it's where it turns, but I don't remember the word.
No, the jerk, right, is the third derivative, but no. So, just because it's continuous doesn't mean you can take the derivative because there might be a sharp corner, right? So, at 0, you actually have two derivatives at exactly the same time. You have a left-hand derivative and a right-hand, and they don't agree with each other. And if the two derivatives don't agree with you at each other at that point, the derivative does not exist. I'm intrigued. What would Desmos do? So, like, what would it do if I said, okay, the absolute value, right here, of x, and then what would this look like? Now, notice the actual derivative does exist, right? So the derivative does exist, but where does it not exist is at 0. Every other number, it's either going to be +1 or -1. Kind of looks like a step 1 a little bit, right? But if I said, what is it at 0? What does it say? Isn't that nice?
Whoa.
I know. When I grow up, I want to be Desmos. All right. I'm going to stop this video.